What we're going to do today is start our unit on complex numbers, and we'll use trig to do operations with complex numbers. And this is going to translate into vector operations as well, because we can express vectors in polar form, and the polar form of a vector can be quickly written in complex form, and the operations that take place with vectors are going to be a little bit more simple if we're seeing them as in complex number form rather than in vector form. So that's what we're going to be having a look at. All right, so what we need to do start off with is get some basics. Okay, first of all, what is a complex number?
Isn't it like a... Oh, it's a complex fraction, never mind.
The entire number system is called the complex number system. Okay, so at the top of our chain here we have complex numbers. There's two subdivisions for complex numbers. What are those two subdivisions?
Real and imaginary.
Yeah, we have the real numbers and we have the imaginary numbers, right? So over here we have what's called the imaginary numbers, and those involve the square roots of negative values. If you take the square root of a negative number, the outcome of that is it's an imaginary number. It's not a real number. Okay? And the real numbers are the other division of complex numbers. And we can further divide the reals into two big categories, rational numbers and irrational numbers. And rational numbers can be expressed as integers. Subsets of the rational numbers would be integers, natural numbers, and counting numbers. All right? Now, integers, whole numbers, and counting numbers. All right, so that's kind of most of our math life, or most of your math life, you've spent right here. We did some imaginary stuff, finding the solutions of quadratic equations that have imaginary solutions. You did that in Algebra 2, and we did that in college algebra. But most of the time that you've spent has been right here. We're going to spend some time here for a couple of weeks, just dealing with complex numbers and how we can use trigonometry in relationship to complex numbers. Okay? Now, so a complex number, every complex number, can be written in what we call a standard form for a complex number. The standard form of complex numbers is A plus BI. A plus BI. Every complex number, which is all numbers, can be written as A plus BI. All right. If A equals 0, the number is what we call purely imaginary. In other words, it only has an imaginary component. It does not have a real component to it. Because A plus BI, A is the real number component, B is going to be, or BI is the imaginary component of this complex number. Because the complex numbers are made up of real and imaginary numbers. Okay? If B equals 0, the number is what? We don't have an I, the number is what? Purely real. Yeah. Okay? And just for example, we could be talking about the number 2 minus 3i. 2 minus 3i. What is the real component of this number? 2. Right. And the imaginary component is negative 3i. Remember, the sign in front of the number goes with the number. Okay, so this number is 2 minus 3i, and it is 2 is the real component and negative 3i is the imaginary component. What about 1/2 plus 2/3 I.
Real 1/2.
The real component of that number is 1/2, and the imaginary component is
Was
2/3 I. Okay? Now, we can graph real numbers. Where do we graph real numbers? Somebody? On the
number
real number line, right?
line.
The real number line, we can graph real numbers. And we can graph complex numbers in what is called the complex plane. Okay, the complex plane is where we will graph complex numbers. And in the complex plane, we have a vertical axis and we have a horizontal axis. The horizontal axis is the real axis, and the vertical axis is the imaginary axis. Okay? So where do you think, if that's based on that, where do you think you would find this complex number, 2 plus 3i?
Where they meet, maybe, I don't know.
Where do you think it would be? What's the real component of the number? 2. The imaginary component, 3. So right there is 2 plus 3i.
Yeah, that's why I had that zero.
If this were in the rectangular plane, it would be the point 2, 3, right? We're talking about points here, but we're really talking about a number. The imaginary number 2 plus 3i is where the real component is 2 and the imaginary component is 3. Okay. Now let's do one more of those, and then we'll talk about one other brief concept, and we're going to be done for today. What would -1 minus 3i? Where would that one be?
That side.
The real component is -1. The imaginary component is -3, so we would be right in that region. That's -1 minus 3i. Okay? You can handle that, right? Now, here's what maybe is going to be just a little bit challenging, but not very. The next thing that I want us to be able to do is to define and calculate what we mean by the absolute value of these things. What do you think we would mean if we were talking about the absolute value of 2 plus 3i? Absolute value of 2 plus 3i. How do we take the absolute value, or what's the definition of the absolute value of a number, a real number?
The distance from zero.
Distance from 0 on what? On the real number line, right? So the absolute value of a real number is the distance from 0 on the number line. Where is 0 in this imaginary plane? Because the definition of an absolute, the absolute value of a complex number is also its distance from 0 in the complex plane. But where is 0 in this complex plane going to be? Where the two lines meet. It's where
The origin.
the origin, yes, it's right there. So to find this distance, and the distance is always going to be positive, just like it is on the real number line, the distance from the origin to this point, we're going to use the good old
Triangle.
Pythagorean theorem. To find the distance from the origin to that point, we're going to use 2 squared plus 3 squared and the square root of that. All right, is everybody okay if we skip the d squared equals a squared plus b squared? And that's going to give us 4 plus 9, which is the square root of 13. All right, now this absolute value, the absolute value of a complex number, can also be called the norm, N-O-R-M, of the number. And when we are working in the context of vectors, it can also be called the magnitude of the number. Okay, a vector has two components. It has a distance and, a direction and a magnitude, a length. All right, so y'all remember that from Despicable Me Part 2, Vector, the evil guy? No?
Wasn't he nice?
No, he was the bad guy.
Remember he was a really nice bad guy?
Huh?
Like, isn't that movie like
Vector!
They're all bad guys?
Yeah.
Yeah, different. It has a
He's the bad guy against.
direction and a magnitude.
Oh!
All right,
Yeah,
so,
that's what I thought it was.
Anyway, if this were the norm of, or the absolute value of just a generic, any old generic complex number, the formula is that it is the square root of a squared plus b squared. And we get that directly from Pythagorean theorem with a distance formula. But the norm, or the absolute value of a complex number, the magnitude of the number, is the square root of a squared plus b squared, where a is the real component and b is the imaginary component. So what would this other number be? That's kind of confusing there. That looks like 4 instead of that. Negative 1 minus 3i, what would the norm of negative 1 minus 3i be, or the absolute value of that be? It will be equal to square root of negative 1 squared plus negative 3 squared, which is the square root of 10. Okay, easy enough? All right, let me grab your assignment sheet. That's the only thing we're going to be doing for today. Sketching the graphs of complex numbers and finding their absolute value.